From South Bend, Indiana, welcome to 3Degrees Discussions. I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders in the 3D printing industry.
I think I saw a couple recent surveys and even older surveys, right, of what's needed in additive manufacturing. And that one of the top, one or two, it's better materials, right? We want better materials for additive. And so when I look at this landscape of what materials are available for additive, well, they're typically commercially available materials that have been converted, sometimes not converted, but typically, modified maybe in some way, especially like FDM plastics, right? There's a lot of changes there, but there's not a lot of materials that have been developed explicitly for additive manufacturing.
That was Nick Sonnentag. Nick founded Sunnyday Technologies in 2023 and converted his basement workshop into a fully functioning concrete additive manufacturing lab where he works several nights a week to test, create, and modify binder systems for 3D printing. Nick currently works at Oshkosh Corporation, where he leads efforts to integrate advanced manufacturing methods and materials into heavy-duty automotive applications with a strong emphasis on large-scale 3D printing technologies. This included work with the Oak Ridge National Laboratory to investigate and develop a construction 3D printer system for Portland cement-based mortar. Nick holds a Bachelor of Science in Material Science and Engineering from the University of Wisconsin-Madison. Before we get started, head over to www.3degreescompany.com and subscribe to the podcast. Remember, you can listen to your show anywhere you download your podcast, including Spotify, Apple, Amazon, or Stitcher. Also, if you or your company are looking for materials, qualification, or general additive manufacturing support, reach out through the team or our website via email at info@3degreescompany.com.
All right. Thanks for joining me, Nick. I'm really excited for the conversation. I think we've been talking about this for years, but I'm excited to have you on. So like we do with everyone on the podcast, we'd love for you to give the audience kind of an early stage background. So where are you from? Where'd you grow up? What do you remember of those kind of early seeds of inspiration that got you down the engineering path?
Thanks, Mike. And thanks for having me on the podcast. I really enjoy listening. It's a great way for me to catch up and hear about, old colleagues and what they're doing and learn about others in the industry. So it's a great service. I appreciate what you do. And so my background, I'll try not to spend too much on the very early years, but I'll say, it's sort of an interesting piece. I have three older sisters. And when I was about 8 years old, I wanted to get a train set. And they said, well, if you're going to get a train set, you have to be an engineer. Engineers have to be good at math. They have to be good at science and chemistry. And so, I was hitting the books pretty hard to get that train set, only to learn later they were, going into college at the time. And they were seeing all these engineers that had great job prospects. So they helped me lay that foundation. I sort of studied hard in those areas. I really loved chemistry a lot. Nearly went into chemical engineering. And then when I went to Madison, I was sort of looking at the chances or opportunities there with their different programs, and the material science really appealed to me. As I looked, sort of historically, and we judge sort of eras on the Bronze Age, the Stone Age, and so I saw materials as maybe a way to leave my mark on the world and contribute to society. And so I studied in those areas. I had some really great experiences. I got to work as an intern at Harley Davidson for some summers. Got one opportunity to work at Oxford Superconductor. Did a brief intern hourly position for David Larlestier, who's a world-renowned superconductor researcher. And so you look back at those opportunities, and it's just sort of happenstance, right? That I got to do that. But and now you look at, wow, what an incredible opportunity. So after that, I was studied mostly in metallurgy. My first job was actually DuPont. After 9/11 happened, actually, the aerospace industry had taken a turn. I graduated around that time. And, I was hoping to find something in aerospace, but a lot of engineers were only working, part-time hours. So I went to DuPont, and that was an incredible experience. I got to learn a lot about formulating extrudable granules, which at the time wouldn't seem like it has a lot of application, but now that I'm working in additive, it means everything. So I got to work there on formulations, basically putting together, what extrudes, what doesn't, how to process things from a lab scale up to a full, tonnage of material. And they really had just great systems for safety, for um, uh, intellectual IP generation, right? Like their sort of research engine, how they came up with new materials and new compounds, and then brought those to commercialization. It's just a really great experience. So I did a few years there, and then an opportunity came up back in Wisconsin, where I'm from Muskego, a little town south of Milwaukee. And so I came back to Wisconsin and got to work. At that time, it was called Lattice Forging. Now it's ATI, Allegheny Technologies Lattice. And that's where I really started to get an experience with additive manufacturing. I worked on some government programs that were focused on, sort of looking at new technologies. And while I wasn't participating in those directly, I was sitting in those same committees, the technical committees, overseeing those programs and seeing what the capabilities were of additive. And it was just mind-boggling what was possible. Now, from a forging perspective, we were making large, hundreds, thousands of pound forgings, and so it really didn't have any application there, but we knew, it has potential. Of course, ATI today is making those materials. So I spent about 12 years there, working on material programs, doing superalloy, raw process development and heat treatment development. Got to work a little bit with titanium aluminides, as well as large aluminum forgings for launch structures for NASA. So it was just a really incredible experience, and we did some movement. My family, we moved further north up to where we are now in the Green Bay Appleton area, called the Fox Valley of Wisconsin. And one of the big employers here is Oshkosh, and so that's how I sort of got in there. And when I first joined the group, there wasn't a lot of interest in additive. This is about 2016, 17. But as the years went on, there was more and more interest, and now we're looking at programs of where we can apply additive manufacturing in those vehicles, and it's an interesting application. But we can get into that more. That's a little bit of the background, I should probably mention too. 4-H. 4-H was a huge part of my education, in school, but sort of being a farm kid, I grew up on a horse farm, not your typical farm. It was a business, and you sort of got that exposure that you realize later, how it all fit together. But 4-H was a great way for me to get out, beyond school, do a lot of public speaking, and sort
for
of
those in the audience who aren't from the Midwest, do you want to explain what 4-H is?
Yeah.
Being from Minnesota, I know, but
yeah, 4-H or FFA, Future Farmers of America, will often get confused together. But 4-H is sort of it's a program, along the lines of Boy Scouts or Girl Scouts, that you're looking to sort of teach life skills. They have different areas. I did rocketry, right? So you're learning about some aerospace stuff early on. I had chickens growing up. I showed horses. I was on a horse farm, so we did all of those parts. I crocheted things, which I don't know, depending on how you look at it, might be the original 3D printing. It just wasn't digitally controlled at the time. So yeah, you really got a lot of exposure, and I think as an engineer, you can't pass over that hands-on experience. So all of those things, you sort of learn how things work. I had to make things every year for the county fair. And then you're judged, how you perform. So it wasn't just a pass by, you had to physically make things. They were judged on their quality, and if you did good enough, it went to state fair. And so it was all an experience, and I think really great growing opportunity. And at the later stages, especially, you got a lot of leadership camps and leadership experiences. One of the reasons I got to go to Madison, that it was so easy for me, even though it's a very large campus. I know at the time my parents were concerned, right? Little farm kid going to this big school, but I had already been there 4 summers with 4-H doing different leadership camps. So I spent more time on that campus probably as a teenager exploring and seeing all the different parts of it than I did when I was a student. Because when I was a student, I was busy. I was studying. I was an engineer, right? I wasn't, going around all the little fun places. So that 4-H basically gave me a line into college, and made that transition very easy. So I don't want to leave that out of the picture. Is a big part of my life.
And so when you're at, it was ATI that you kind of first heard of, saw additive manufacturing. Do you remember kind of what what type of printer you saw? What was it? Were you in person? Were you running any machines? What was, do you remember that kind of first kernel of inspiration?
Yeah, absolutely. So we were participating in a program called the Materials Affordability Initiative Consortium. It's an Air Force and public sponsored program, depending on the type of funding that's going through. But those programs were looking at early stage sort of additive. They're looking at SLA printing of molds for like airfoils, and other applications. And so I wasn't working directly on those programs, but I could see as basically a competitor to conventional forging, casting, the business of ATI at the time, where these applications would be. Meanwhile, going to all the conferences, learning how, forging, right? We're trying to architect grain structure and grain flow to improve the strength of materials. And then, I'm seeing, digitally, people putting down powder and architecting these same sort of like grain flow patterns. Still something maybe we haven't perfected quite yet, but, the potential is there to do it, which, when you're sitting there and you reflect back and you think, this is sort of a monumental change, right? It's a sea change in how we as human beings can produce matter. And that's just, it's sometimes too profound to sort of think about, because it's just that the capabilities are so immense. And that's, I'm glad there's tools out there like generative design and all the other computational, sort of helpers there that we can do today to help us sort of visualize how these models can be made better. But that was the opening door, right? And that committee was very focused on saving cash for the American taxpayer, right? The entire purpose of that group was to, find methods to reduce the tax burden, of the Air Force, of making it easier to maintain, lower cost to maintain, improving structures so they lasted longer or had improved capability. And so it was very competitive. And so you got to see exactly how those additive methods would compare to conventional. And if they didn't compare, they were dropped. And the ones that were good made it through and had a completion. So it was a great way to see, as the industry came together as a whole, you got to see, competitors sort of comparing notes and seeing, how can we use this technology? And that really sort of laid a great base for me to say, okay, I'm familiar with forging, very familiar with forging, somewhat familiar with casting. And, here's another process. How does it fit into the mix? Where would you use it? Where does it make sense? And yeah, it was a great interest, but you're right. I wasn't having hands-on experience at that time.
And I imagine too, like as you transition to Oshkosh and kind of other parts of your career, those same types of questions come up, right? If you're evaluating the technology for cost, speed, ease of use, how pervasive is it in the supply chain? I think that's stuff we're still navigating as an industry.
It's every case is so distinct. The interesting, the business case for Oshkosh is that it's not millions of vehicles or even hundreds of thousands of vehicles. Typically, a lot of the vehicle lines that we have are in the thousands per year. And so, that's really a nice sweet spot for additive, where it's enough vehicles that you can spread out the cost of development, and all the modeling, the design for additive, as compared to, one-offs and things where maybe for NASA it would make sense because it's a highly valuable structure, but it just wouldn't be cost competitive for an automotive market. So yeah, it's a great perspective to have. I think it's a very different, a lot of people have come into the industry only knowing additive. And a lot of people go into companies only knowing that one company. So when you have those different perspectives, it really gives you some perspective on knowing, is this really going to be competitive? Where are the pitfalls? What are the parts that they're not quite telling you? And sort of being able to sort through all that to find the value. It's a lot.
Yeah. And as you, I mean, you are kind of at your core a materials engineer. Were there other skill sets as you got more intimately involved in additive that you've had to grow or kind of that may have been underutilized or under developed as you kind of first started your career?
Oh, all of them, right? We get out of school and we sort of have a tool set, but it's not sharpened yet. So we kind of pick those individual areas and see where we can get better. I think one of the big ones, and I tell this to all the designers and manufacturing engineers, it's like the materials engineers, we work on the materials, we make them better, but then we sort of turn them over to mechanical or design engineers. I say they get to have all the fun. They make the parts, they make the magic. And that's part of it. As I've grown, I can't occupy all of their time, so I have tried to pick up some of those skill sets on my own so that I can sort of explore the design space. Instead of taking up their time with, hey, how does this new material, or if I make this tweak to modulus, how is that going to affect the generatively designed component? Is it going to really make a difference in the stress profile, or is it just perceived that it's going to have that impact? And so those are definitely some skills. I mean, things like Python, right? That's out there that I've seen in materials engineers that typically, you don't see a lot of cross-pollination between computer science, data science, and materials engineering. But when it does happen, it is so powerful, for studying and looking at, what new materials are out there. I think that's one of the biggest sort of fundamental pieces that we can see in our current age is that there's a lot of different combinations of materials. Thus far, say metals, right? We've only been able to develop the metals that are produced typically using very large industrial processes, casting a 36-inch diameter ingot, which includes a lot of constraints on cooling and making sure it's not going to crack and things that go along with that. Whereas additive, right, we have things that are cooling in fractions of a second, and so really opens up that box. And so I would say finding those additional computer skills using things like image analysis, Python, anywhere that we can sort of spread and understand better from a material scientist standpoint how our work is being applied. So then we can be better material scientists. We can say, okay, well, this isn't really important to the designer, right? One example is strength in society, right? Everybody's going, give us a stronger part, give us a stronger part. But a lot of times the failure happens in ductility. And so, people are fighting for, I've had this happen where, we'll check out a new weld alloy and they go, yeah, this new weld alloy is way stronger than the old one, but the parts keep breaking. We're like, it's stronger, but right, the old one bends, it doesn't break. And so it gives you that perspective. It also lets especially from the mechanical design piece, is that it's not always a materials problem, right? We could do this, we could do that. It would be very expensive or costly or time consuming. But what if we change this small aspect of the design to reduce the stress riser? Hey, we solved our problem. The part stopped breaking. It's so, it gives you perspective to know when to stay in your lane and when maybe you can start, looking at some other opportunities and where it might work.
And so kind of the other evolution of your career that you haven't really touched on yet is kind of the concrete printing. So do you want to talk a little bit about kind of that effort? Because I think I have a ton of questions on that side. I'm sure the audience does too, with some of the stuff you've put out and on LinkedIn and other places. So how did that start and kind of where are you with that today?
Yeah. It's a big question. I'll start with one thing, and if you've talked to me at an additive conference, I'm a material scientist, and so I'm advocating for better materials. I think I saw a couple recent surveys and even older surveys, right, of what's needed in additive manufacturing. And that one of the top, one or two, it's better materials, right? We want better materials for additive. And so when I look at this landscape of what materials are available for additive, well, they're typically commercially available materials that have been converted, sometimes not converted, but typically, modified maybe in some way, especially like FDM plastics, right? There's a lot of changes there, but there's not a lot of materials that have been developed explicitly for additive manufacturing, right? And I understand that. I'm coming from a commercial aspect. I worked for all these big companies. You have product, you have to be making profit. There's constraints. There's equipment. You can't just turn everything off one day and switch to a new product the next. So I saw it, as one way. It has to be commodity materials, right? They have to be available in bulk. They have to be easily accessible. They're not going to be expensive. So if I'm going to be, dabbling in these materials, it's a good place to look. I should start by saying one of the reasons that I got into it at all, Oshkosh did a brief work with Oak Ridge National Labs. I have them to thank incredibly. Their promotion and helping of the U.S. industrial base is just incredible. Just awesome technology coming out of there. Very helpful people. Very great to work with and open. And so I think that I have to give them a lot of accolades for inspiring me to start doing that. So Oshkosh worked and made a large 3D concrete printer. But as I said, my area is the materials. And so after that was done, I usually never had the opportunity to take my work home with me. No matter how interesting it may be, it's technically too challenging, or the equipment, or just, IP wise, I'm not allowed to take it home. But in this case, my current employer is not making cement. And so I was fairly safe to go off and they let me do that on my own. And so I started doing this on a small system at home, and I was thinking, okay, there was an absolute explosion of materials research on printable concrete formulas, especially low carbon embodied, using a lot of recycled materials or reclaimed materials in those mixes. That just an explosion that happened after about 2019. And so, going through all that literature, watching everything that's online, there's some really great companies around the world that are doing this, and sort of learning from them on how to do it. But I wanted to focus on smaller things. I mentioned before, right? So while one side, I can develop materials explicitly for 3D printing that are made very targeted for that. Now, the second point is that I know the better the performance of those materials, the more efficient the design can be. And so that was sort of a board that I was able to use to say, okay, now I need to train on modeling software. I need to train on some design software so that I can start understanding how these aspects interact. And so you kind of get this continuous loop of, okay, let's improve the materials. What are the important critical properties? Is it compressive stress or strength of, that's what typically we do for concrete, but I will say typically I'm looking at bending stress, right? If we're looking at very complicated concrete design, some things that have really high overhangs and very thin sections, you're really looking more at the bending stress. And so it helped me work through those issues again of does it need to be stronger? No, it needs to be more flexible. And so it helped me in those pieces. And then just overall, right, I'm looking at my career. I'm saying, when I was at DuPont, that was sort of an opportunity to help feed the world, as in crop protection. So you're helping, establish the food base. At ATI, I was helping, with the defense of our country and getting things into space. And, at Oshkosh, you're sort of doing a lot of the above. Our old logo is protect, serve, advance. And so you're seeing all these opportunities sort of come to a head, and how do we better advance that? Well, concrete can serve as a lot of different infrastructure. I'm not really looking at printing houses right now. This is small items, but I want to find it's really about distilling out those aspects of 3D printing in this type of technology for concrete, because it comes right back down to the same principles. We know 3D printing is typically more expensive, and concrete's the same way. So how do we make these products more valuable? What additional performance pieces can they offer? What additional functions, instead of just being a wall? I posted a planter wall, but it also has integrated watering underneath. And so, what problem does that solve? Well, people have these smart watering devices, but typically they're using a plastic container. They put it outside, it's good for a year, it gets UV degradation. Now your big tomato plants that you had last year, now it's just a big mess on your porch. And so, I'd done those, went through that pain, and I said, great, well, if I make it through concrete, this is going to last for 100 years. And so, I just kind of replicated that, but and at the same time, I wanted to look nice. That what was previous in that spot were some cedar planters. They degraded after 7 years and they just fell apart. And so, we don't have that worry anymore. Want it to be integrated with the shape of the landscaping there. And I'll be posting pretty soon. So the backside of that you can see is printed. The front side has been finished to look just like rocks. So that's going to be a sort of a fun piece of it. So that's sort of, bringing in the aesthetics, even dual aesthetics of a natural on the front, a more contemporary in the back. It's functional because it gives the plants water. Some of those planters would run out of water very quickly because some would get hotter and sort of, let all their water out. So it's really, trying to find the value in all those pieces. And then formability. Right. A lot of the concrete printing we see is what they call one part. So you add water and the clock is ticking as that material hardens. You can try to make it as stiff as you can. Maybe you can make it sort of like a clay, so it'll build to a certain extent. But you're limited. And if you have any sort of issues now, if it sits in the hose, you have an entire hose full of concrete, and that's not a problem you want to have. You're probably throwing it out. So newer technology is called 2K, two component, where you add an accelerator similar to how shotcrete is applied. And so you can keep your material fairly fluid until you are ready to print. And so another video I had posted on LinkedIn shows I'd printed off the word nothing. I was trying to test out start and stop. It's difficult with concrete. It wants to keep flowing. You have pressure in the line. So once you can hit stop, but the machine will tell the pump to stop, but a little bit more is going to come out, and that's compensated though. Yeah. And that's part of the fun. When I did start doing more with 3D printing at Oshkosh and started working on those programs, I followed what I heard, GE engineers did. When GE engineers brought in 3D, they gave them all 3D printers so they could learn firsthand how to do it. I like to talk about, forging and knowing things firsthand. There was a process where, from the print, it looked like it was, hey, we do this forging process, we do this, we put some oil on, and then, we forged your part. In reality, though, when you went out and looked at that process, it was a reverse extrusion. So they had to put oil in the pot. They put the piece in. There's this giant flame that comes up, and then the operator had to reach through that flame or somehow get this additional piece of ceramic so that the dies wouldn't stick. You don't see those details that are very important from the print. And so, when I finally got an FDM printer, I ripped it apart and rebuilt it basically with all new components, got into the firmware, wanted to understand all the software aspects. I did when I was at Madison, I nearly double majored in computer science. I love computer science and still, this gives me another sort of opportunity to work in that realm. But I just stuck with materials because that was challenging enough. But now I get to sort of go in there and do a little bit of semi-coding and you can see what effects are on the firmware, what effects are coming from hardware changes. Was it just a loose screw or a loose line somewhere that you thought was a software problem? And sort of getting all of those skill sets is really useful. It helps me sort of, again, you're growing, you're learning what other people are expecting. And it helps you just be a better engineer.
And do you want to walk through kind of the machine that you've built and kind of give a size of scale and like, okay, I've got to get 20-pound bags of mix, and like just walk through, kind of give people like a visual idea of what you've built and kind of how it works.
Yeah, absolutely. So, um, the printer I'm printing on is about a 4 cubic foot gantry unit. It's a dual Z, dual Y. It has a single motor on the X and then an extruder. So we're up to 1, 2, 3, 4, 5, and then 6 motors. I have an 8 port. I use a commercial off the shelf Octopus controller board, which has 8 ports. I use the 7th port to control the pump that feeds material through. So this is a progressive cavity pump made by MAI International, sort of customized for 3D printing materials. It does have some limitations, right? I can only use, depending on the head that I have on it, either maximum 2 millimeter or 1 millimeter grain material. And that's going to pump it through to a print head. Now, a lot of 3D print heads will just not have an extruder there, right? It's just a pipe, and you can pipe it right on. Because I'm interested in getting, I understand it from a sort of a base concept of 3D printing, right? The advantages are with design freedom. And so I was working with 1K and sort of getting that going, and it works a bit. We can get 12 inches. You see, when you see house prints, you'll notice that the dark region that was just printed is maybe a foot high or maybe 18 inches, but they're not going to push it much higher than that. But when you get to the 2K mixes, when you can start hardening that from the bottom up, you can grow systems that are 2 meters, 3 meters high. So I use a screw type of extruder on that end for the print head that allows mixing of an accelerator there. And so that's sort of the general setup. When I'm mixing materials, right, it's difficult. These systems, and I've heard this from a lot of people that are printing concrete, the systems that are out there for concrete are meant to deal with somewhat liquid materials. A lot of your barrel mixers are depending on sort of the rock aggregate in there to get good mixing. And so if you just have sand, you're not going to get that good mixing. So my time when I was at DuPont taught me a lot of different mixer techniques and ways that you can make sure you have very uniform blends, because the products I was working on, if you had a bad distribution of your technical material, you're going to kill crops. And so, and this is an industrial scale. So not, a couple acres, it's thousands of acres. And so, having that perspective really helped sort of understand when I was going through picking out machinery, what's going to work, what's going to give me, consistent mixing. So you can use a planetary mixer, sort of like a really big KitchenAid mixer. That's what a lot of cement, when I'm doing subscale batches and a lot of, many of the cement, research groups are using those at subscale. But then when you get to larger scale, it doesn't really transfer, right? I can't lift 100 pounds in a big, in a big bucket. I'm not that big of a guy. So, you got to get other parts. And so there's mortar mixers. I use one of those. It works fairly well, but it's definitely an area that needs improvement. So depending on my mix, I'll put it through the slicer. I'll see how many pounds I need. I know that I need a couple extra pounds, for losses, for getting the system started up. What's going to be lost in the hose on the way there. So I'll get that all mixed up. I'll get my system set up. But it's a process. Maybe someday I won't have to be making my own materials. Maybe I'll be buying them. It certainly would save me a lot of time. But at this time, it's cheaper and efficient for me to get some. And like I said, I'm enjoying it because it gives me direct access to turn all those knobs and say, okay, if I include a little bit more sand here, I use a different type of sand. What if I increase the amount of clay or whatnot? The types of cements that I'm looking at are not your typical cement. I am focused on a type called LC3, which, if you're looking at the worldwide supply of materials, clay is very abundant. When we talk about low carbon cements, people bring up all the time, they talk about fly ash, which is a waste product basically from coal, energy production. They'll talk about steel slag, an industry I know well. And so you can get those. However, When you actually get into the logistics streams for those, you'll realize that those are used up. The roads that are being paved and the buildings that are going up are using all of the slag, all the fly ash. They're looking for ponds and things, right, where they've disposed of this and they can reclaim it and use it again. But that material is all used up. The clays, though, are abundant. They're one of the most abundant materials in the world, specifically kaolin clays. And this is the same stuff used to make porcelain. But of course, if we're making cement, we don't need the very high quality porcelain clay. It doesn't have to be transparent white. I can deal with a lot more iron in my clay than that. But the important thing is that clay requires about half of the energy to turn it from being a kaolin to a metakaolin. And that metakaolin is incredibly effective as what's called a pozzolan, which basically works in step with the cement to create a binder system. Now it's LC3, limestone, calcined clay, and cement. And so you still have some Portland cement in there. And so, those are sort of the areas that I see as being useful to develop, because it's not just, a distinct one piece solution. It's where we go. And there's another really interesting piece that I learned when we were doing the program with Oak Ridge is that the material supply, right? I'm concerned about logistics. I don't want to just do this as a one-off. I want to know, how does this go if I want to distribute and start growing this business, across the US or around the world. Your supply for concrete, it's a common material, but everywhere it's made, it's individual, because you're not going to ship aggregates, your rock, your sand over, a certain distance, because then it's not cost competitive. And so in the same way, when I'm looking at these 3D printable solutions, I want to find solutions that are using local materials. And so that's what I'm doing personally. I'm using local sands. Happen to be very lucky that the area in Wisconsin where we're actually has a lot of mining for frac sands. So we have some very good sort of high quality, well sorted sand products that I have access to. But I think, as we look at growing it.
When you say that, like, do you just know a guy that can get you some like high quality sand, or can you like go? Because that's always curious about manufacturing, all the like loose ends that kind of you end up learning about in these random parts of and random nondescript buildings, right? So how does that work? Or if you can divulge your secret, like, do they just sell it because it's geography wise, like it's there, or you have like access to? How did that work?
Yeah, no special access. What I'm looking at whenever we're talking about like 2 millimeter and 1 millimeter, those are somewhat standard grades of sand, what they would call probably a medium grain and then a fine grain sand. So you can buy this stuff. As I've gotten more into the industry, there's are certainly suppliers that have this available. That it's they are doing it. I happen to find I called around. This is sort of you got to put boots on the ground, get out there, do a bunch of phone calls, visit the people. I mean, when I started out, like anybody else, I went to Home Depot. I got some play sand, and I'm like, hey, is this stuff going to work? I was sorting it myself, right? I'm putting it through screens, taking out everything over 1 millimeter, 2 millimeter, but it's exhausting, right? And as we know, the time you put in, like personnel time, is probably one of your big cost killers. So you always want to try find ways to reduce that. So I was able to find a source locally that had some sorted sand that was very clean. That's important. You can't get a bunch of junk in there when you're trying to hold scientific experience to compare different materials. It was clean, it was sorted, and cheap. Probably one of the most important things. So instead of paying, $10 or $5 for a bag of sand at Home Depot, it's like, 10 or 17 cents, depending on the grade of sand that I'm getting. But again, that's something and I think others in the concrete printing area, they've found what substitutes they can get, whether it's grit blast media that's well sorted and made for that purpose. But it is, it's such an early, I like to say it's similar to maybe additive manufacturing industry 10 years ago, maybe further, maybe 15, because it's so much at the infancy, but there's so much fun and development that can be had at that point.
And where do you see for your system and kind of your business growing? Like, what are the kind of applications and parts that you've kind of honed in on or you've gotten interest for?
Right. So I'm taking a bit of a game theory approach. If we look at how we make parts, and this is something, right? Again, I'm looking at all the different additive manufacturing methods, and we can make a lot of really small stuff. At Oshkosh, I'm interested in making big things because a lot of the things that Oshkosh makes in-house are structural, like a cab, a chassis, right? These are starting at maybe 3-4 feet and getting larger. And there's not a lot of additive methods to make that sort of thing. So when I looked at the concrete piece, right, there's people printing houses, and I'm not printing houses. That there's
Right.
there's a lot of steps between here and there. But on the same scale, right, there's people printing clay, and I have a clay printer for doing some subscale things that I can figure out. But in that interim area, right, the game theory of, okay, well, there's a lot of small stuff, there's a lot of large stuff, but who can make things in between? I was like, well, this is great. And so this 4-foot system can make, again, when we're talking about how high can you build? Well, when I got the system, I was thinking just 1K mixes. If I can only build 18 inches high, it doesn't matter if I have a system that's 8 feet high. I'm only going to be making parts that are 18 inches to begin with. And then I guess on top of that, what I really want to do with the system is explore that design for additive manufacturing space. Because that's really the critical part that makes it successful or it doesn't. We see still today a lot of people, will come to me and say, "Hey, can we make this part in additive?" And it's sort of the same. If you turn it around and say, "Well, would you take a casting, or let's say it's reversal? Would you take a forging and make it as a casting?" No, you can't. It won't have the same strength. It'll break, right? If it's subjected to the same sort of performance expectations. And in the same way, people say, "Hey, can we make this part in additive?" And you go, we could, but it's not going to be the right approach. Let's redesign it to take advantage of what additive can provide to us. And so that's really what I'm excited about exploring. First, the materials and how they can give sort of this continuous improvement cycle of improving efficiency in design, because the stronger the materials or however they're best performing can reduce the amount that we use. And that's directly reducing costs, reducing CO2. And then the third part is how can we incorporate additional functions? We've seen things out of, say, MIT that are showing, can we use concrete as a battery, right? Can we make that house wall that's concrete? Can we put some carbon fiber in there, carbon nanotubes, whatever it may be, and turn it into an energy storage device? Even easier to think of with all the heat pumps that we see going on. Can you make sort of like a heat pump storage device? Are your interior walls, right, hollow, and you can have that part of your heat pump, and other sort of additions. So I want to see how can we get additional function out of concrete prints? Can we incorporate plumbing, electronics? What are the needs of society, and how can we meet those needs with functionalizing these prints? It's not just a structure. I want to make functional structures. It's not just going to protect you from the rain, but it's also going to provide some sort of other ancillary feature. And the more of those features we can add, that is where we find huge value in additive, and where it's going to sell itself. Because if you look at it and say, well, I could get this retaining wall, or we could print it. I mean, if you've built a retaining wall, large rocks are expensive, and they're heavy to transport. Well, these pieces that I just made, I could lift most of them by myself. And then you can come in afterwards. You could fill it in with concrete. You could fill it in with gravel, what have you. But it's just sort of looking at ways that gives us a way to stop mining large rocks. Do we need to do that? Can we just use small gravel and waste streams from other businesses? those are all there. And of course, I've mentioned the LC3s, but there's also geopolymers. And so LC3s are going to be great for things, that need structure. Geopolymers, though, can tolerate a lot of acids. So if we're looking at chemical processing, right? If you want to get a chemical processing plant, we're going to go, you need some sort of high strength tank that would typically made in cement or something. Can we make that out of a geopolymer? Can we include additional plumbing options in it? Those are all options. I think it would be kind of cool to make a pizza oven, right? Because we know conventional pizza ovens have this shape and it works well. That's been around for a couple hundred years. I'd love to see a graduate student, studying CFD that does like an optimized CFD pizza oven, right? So I can cook my pizza faster because I love pizza. What are other misses? It's just you really have to explore your imagination, because I think that's the only thing that's really limiting us now is sort of the conventional mindset that a lot of people, maybe from my generation and older, have with the new generation of workers that are coming through and going. I mean, when I talk to our engineers, many of them have a 3D printer at home, and so their question to me is, why are we not using this technology? Which I usually answer with specs, right? Like I go, well, you need a minimum viable property, right? And they go, yeah, and we don't have that for the material yet. There's some there for aerospace. Let's keep the industry going forward, but that's the big part. I want to see specs, and that's part of what I did when I was at ATI, is help develop those sorts of data sets for specs. And so again, when I'm doing these material developments, I'm trying to look with that eye forward of what's going to be important, what data is necessary to capture, and what's going to move the needle that we can keep on doing better things, greater things in the future.
Awesome. And so, kind of last question as we wrap up here. What's something, a book, a podcast, a movie that has kind of inspired you over your career? Whether that's kind of working in big companies, starting your own thing, doing materials, doing engineering in general, or just in life.
Yeah. I'm gonna pull maybe a strange one here and say video games.
Yeah.
I've been a gamer, from way back, from starting from when I was a kid. We got an Atari. And progressively through, when I was in Madison, they had just installed Ethernet, so that was sort of a free for all for a while as we were playing a lot of Quake. It was, and maybe nobody. I think it's past a time that anybody will get in trouble, but they were running a Quake server on the engineering. What was brand new at the time, I think it was a quad Pentium. So we had this blazing fast Quake server, and we could do all sorts of fun stuff. And we were playing between floors, in the dorms. And so it was a lot of fun. And then, as it went on, like you're seeing in those games, right? This is sort of sci-fi influencing reality. Like, hey, the timing to build your mech, there's a certain time. And I'm thinking, right, as I'm seeing additive manufacturing, I'm like, yeah, right. Like there's the additive manufacturing, and we're talking about, other companies like Orbital Composites, they're going to go do additive in space. And I'm thinking, well, yeah, there it is, right there. We can go build things in space, and they're building the mechs, they're sending them down. And I'm thinking, well, and the other side, right? When I go into work and I see these things that they're doing at the Air Force, and going, they're really creating this technology. And so I think, that's one way that we can be inspired, is sort of looking at those video games and what they promise us for the future, or say is capable for in the future. I've got a lot of great book recommendations I've actually gotten off your podcast, but I can't think of any right off the top of my head. But that would be probably mine, maybe a little bit off the wall, but that's one that I think, as I look to the future, how can we bring that closer to reality?
Awesome. Well, thanks so much for joining the show, sharing your story today, Nick. Awesome to see all the cool stuff you're doing, and we'll throw up links to all the kind of YouTube, LinkedIn, website stuff that you have out there. So thank you so much.
Thanks, Mike. Really appreciate the opportunity. And keep it on. I look forward to the next podcast after mine.